So the lights actually dimmed a little bit. If we could bring those down, yeah, more please. There are going to be diagrams and folks are going to miss out. Brilliant. Okay, so my talk is the charming genius of the Apollo guidance computer. And I am led to understand that there is a prohibition against swearing, and I just want to point out that my shirt says ass. Buzz Aldrin runs a foundation, Second Man on the Moon, that helps people get into STEM, and everyone can go buy this t-shirt, Get Your Ass to Mars. So, charming genius of the Apollo guidance computer. This is the Earth. This is our planet. This is where all of us are presently. There are no people that are alive that are not on this planet. This is the moon. There are no people that are currently alive that are on the moon right now. However, we still have some of the people that touch the moon still living. The moon is about 400,000 kilometers distant. So if you're going to go from the Earth to the moon, you have a bit of a trip. It's about 2 days. We could probably do it a little faster if we had a bigger rocket. But bigger rockets have a tendency to blow up. Speaking of big rockets, so we're talking about the Apollo spacecraft. What we're not really talking about is the Saturn V. The Saturn V is the lift system for the Apollo spacecraft. It's a 3-stage rocket. Here you see Apollo 11. This will be the first experimental mission to land on the moon. I say experimental because they only walked around for about 5 hours and then left. Apollo 12 was really the real deal in terms of, we've gone to the moon, now let's do something. Stage 1 is separating. Stage 1 burns kerosene because we didn't know how to build a big rocket that burned liquid oxygen. Everything else, liquid oxygen, hydrogen. Everything else burns LOX and hydroxide. So Saturn V goes up, drops all of its stages. And then once they've finally achieved orbit, once they've finally gotten around the Earth, there's only a single stage of the Saturn V that's left, and it's stage 3. Its primary job is to kick you out to the moon, but before they do that, all through the Apollo flight, they do these system checks. The astronauts are responsible for asserting that the spacecraft won't kill them on the way. Because the Apollo craft, we designed it in such a way that if the line of fatal is here, the Apollo craft is just shy of fatal, because we were in a rush to get to the moon before the Soviets did. So they make a couple of passes around the Earth, they check out that everything's okay, and then the final stage boosts Apollo into a free return orbit. So are any of you orbital dynamicists? One person. Okay. Okay, so free return orbit. I will explain this. So there is a burn that is made on the far side of the Earth from the moon. It's called the translunar injection, and it's the last thing that the Saturn V LISS system does. It's the last thing before you have the Apollo spacecraft. So the way a translunar injection works is you start raising the orbit. So you extend your orbit from where it is in kind of a little bit of an ellipse, and you increase this ellipse until that ellipse gets you closer and closer to the gravitational body, gravitational well that you want to fall into, and then you have capture. So this is called a free return orbit, and it's called a free return orbit because you get a free return. If in fact your spacecraft pops an oxygen tank and you have to come back, you swing around the moon, which happened in Apollo 13, and then you come back to the Earth and you land, or you crash through the atmosphere, which is what we actually do. The interesting thing about this particular orbit is it was considered too difficult to do. So what we were originally going to do was build a really big rocket, and the Saturn V is so big that if you don't put the right type of concrete into the blast furnace, the concrete will melt and then catch fire. Just from the sound waves, not actually from the flame itself. We were going to build a bigger rocket, and then we were going to go straight to the moon. So it would be a ballistic arc that takes you straight to the moon. Now the problem is, if anything goes wrong in that trip, you are dead. You just land on the moon dead. Or crash into the moon. It's really easy to get through a planetary body. It's very difficult to land on a planetary body. The main distinguishing thing that allowed us to do this sort of free return orbit, it's called the Lunar Orbit Rendezvous, was the idea that we could integrate a computer into the spacecraft. The idea that you can have these complicated astrodynamic shifts or in the spacecraft's path that is moderated by a computer, but we'll sort of get to that. So the Apollo spacecraft is interesting. So you see here on the bottom the third stage, and there are two components to the Apollo spacecraft. One is the command module. That's where the astronauts ride up. They're the couches. It's where the primary functioning of the craft happens. And then you have the service module, and that's the cylinder that sits below the command module. So command module, service module. Now the lunar module, the thing that actually lands people on the moon, sits in the top of the third stage. So once the third stage is spent, on the way to the moon, they pull the service module out, they flip it around, and then they dock the service module and the lunar module, and then they back it up. And the third stage shifts itself a little bit in the orbit, crashes itself into the moon, and then you have the Apollo spacecraft. It is the only non-low Earth orbit spacecraft that is manned that has ever been created by humanity. So you see on the far left side, that is the command module and the service module, and then on the far right-hand side, these are my directions, that is the lunar module. The lunar module is basically an aluminum balloon. It's real thin. So space travel is a tricky business. So in the Apollo craft, you know, if you have a solar flare, you're just cooked. You are dead. There's no way to stop that. If a micrometeor strikes your spacecraft, you are dead. There's no way to stop that. So spacecraft is very terrifying because things go wrong very quickly. But for this talk, because we're talking about the computer, what we're really concerned about are orbital paths. And orbital paths are this narrow balance of accelerations. So if you have a human that's trying to make these complex orbit shifts, and they fire 5 seconds too long, or too short, bad things can happen. So, you know, if you fire too little, you miss your goal. You don't quite get to the moon. And it's not so bad because you swing back around. If you fire too long, you also miss your goal. And this is bad because now you're orbiting the sun. And you either want to orbit the Earth or the moon, and not ever the sun. So the guidance control system of a spacecraft must answer 3 questions. It's very important that it's capable of answering these questions. Which way is up? Which is a weird question to ask in space. So we just kind of made an arbitrary frame of reference. We took a couple of stars and we said, that one's down and that one's up. So that's the universal coordinate system. And through the trip to the moon, we actually have reference shifts. So if you're in Earth orbit, we say that north is Z, and then as soon as you leave Earth orbit, we say that Polaris is Z, and so on. But there is an up. Where am I? So you kind of have to know that you're actually in a spot, and then where am I going? So you have to know where your position is shifting. And if you can't answer any one of these questions, you will die. So Apollo, because you have to be able to answer these questions, has triply redundant means to answer these questions. So the first is the most interesting to me. It's called the Deep Space Network. It's basically giant radar dishes scattered all over the planet that bounce telemetry off the spacecraft. And it's able to, because of the relativistic differences between the time sync of the radar, be able to triangulate the position of the spacecraft extremely accurately. If we'd not had the Second World War developing radar, we wouldn't be able to do this. Interestingly enough, this was the only means that the Soviets had to determine their spacecraft's position, because the Soviet cosmonauts were really just people along for a ride. It was a fully automatic system. So it's a global network of long-range radar stations. And I don't know if you've ever seen one of these, but they're gigantic. You can actually use them for radio telescopy. And in the 60s, which is when we're talking about, they're just sort of scattered. Right now, what we do is we've extended the Deep Space Network, and we have put things outside of the orbit of the moon. Nothing had ever been outside of the orbit of the moon, so you have no ability to use that sort of thing in the Apollo craft. The interesting thing here is if you go behind the moon, you lose contact. So if you ever watch, say, Apollo 13 or something like that, there's the dramatic moment where they've lost radio contact because they've gone behind the far side of the moon. So the Apollo spacecraft on the service module has a high-gain antenna. So this antenna is what the Deep Space Network is using to communicate back and forth with the spacecraft. And in particular, it does one thing that is interesting to us. It updates what's called the state vector. So the state vector is really just a vector of positions and accelerations. And so the ground will periodically send to the spacecraft the update for its state vector and say, you are right here. So that's one method. So the other method is very interesting to me because it's so old. It's celestial navigation. So if any of you have never used an astrolabe or you've never walked outside with a sextant, I highly recommend that you do that. It's fascinating to be able to determine your position by just taking the angle of a couple of stars. So the Apollo spacecraft actually has all of the equipment that you need to do celestial navigation. It has a telescope, and it's not really much of a telescope. It's actually a 1x magnification telescope, so it's really just a window. And it has a sextant. So the question becomes, if you're in space, how do you sight? You know, if you're using a sextant on the planet, you have a very convenient horizon, but there is no horizon in space for you to be able to sight off of. So they have mission-timed star charts. This actually landed on the moon. It's from the lunar module. Each of these little dots represents a star of a certain brightness. And so the responsibility of the navigator, and there actually was a navigator, was to go to the instrument panel and then align the sextant with the well-known stars and then press a button. And that button would update the angle of that star, and then from that angle, compute the state vector. So now you have the state vector being updated in two ways, two independent ways. So if one fails, if a meteor happens to snap off the high-gain antenna, you don't have to abandon the mission, or you don't die. So this is the command module. Down here at the bottom are where the couches are. That's where the astronauts sit when they ride up. Then they fold the couches back, and then they have a place to work in space. And you can see on the far left-hand side what it calls the optics assembly. That's the sextant, and that's the telescope/window. It's not just a window because you can actually fold this thing up. So the navigator just sort of floats up, grabs a hold of it, sights, and that's where celestial navigation happens. So the last method, if all of these fail, there's still one more method that the Apollo spacecraft has to be able to tell where it is, to be able to update its state vector. And that's with dead reckoning. So dead reckoning is interesting. That missile that's being launched is the Polaris rocket. So actually the Polaris weapon. It's a submarine-launched nuclear weapon. Launching a nuclear weapon from a submarine is an interesting challenge because submarines move around. So you have to be able to continually tell the missile where it's going to start from, and then the missile has to be able to guide itself to destroying people. It does this using internal guidance. And I mentioned the Polaris because it was built by the MIT Instrument Laboratories, which also built the Apollo guidance computer. And they used the same methodology that they did for Polaris as they did for the Apollo guidance computer. So inertial guidance is interesting. This is basically a top, but it's an extremely sophisticated top. So what this is three interlocking gimbals, they're called, spinning all the time. And when your spacecraft has any sort of change in acceleration, say fuel is sloshing or a person kicks off a wall, these gimbals get deflected slightly. And that deflection causes an electrical pulse of a certain magnitude, and that magnitude of that pulse then tells the system on the far side, which is going to be the computer, which we'll talk about, how far the craft is deflected. So if you know how far you've deflected, you can now update your state vector using dead reckoning. The gimbals are limited in terms of accuracy. Over the course of a month, they'll go completely out of whack, but it doesn't matter because the spacecraft only needs to be in space for 2 weeks, and they can realign them by using the sextant. They can realign it to the global reference frame. So there are 3 gimbals in this, and if any of you know anything about, say, fighter planes, they also use dead reckoning, but they have 4 gimbals. And they have 4 gimbals because if you happen to have gimbals that come into alignment, if you make a move so that the X and the Y axis gimbals come into the same plane, you've now lost the ability to distinguish between X and Y movement. So that's called gimbal lock. But they only have 3 to save weight, because the Apollo spacecraft is very, very weight conscious, and you save about 50 pounds if you cut out a single gimbal. The challenge here is that you have gimbal lock now. So this is the nav ball, is what they called it. It tells the pilot of the craft what their orientation is relative to the standard reference frame that they're operating in. And at the very top, they had a big red circle, and that red circle is gimbal lock. So if you hit that, you've now lost the ability for the spacecraft to update on its own its position, and then you have to realign the thing, and it takes an hour and a half. So they avoid it as much as they can. Apollo 11, gimbal locked. Apollo 13, gimbal locked. Apollo 16, gimbal locked. So the person that designed the inertial guidance unit deeply, deeply regretted saving 50 pounds. It ended up not being worth it. So that's where the dead reckoning happens. So the command module is relatively small. It sits exactly below or off to the side, depending on how you're orienting yourself, below the celestial navigation. So the Apollo guidance computer is responsible for integrating all of these things. You know, this is a very complex spacecraft. It is possible to fly manually. The astronauts can do it, but they can do nothing else, and they're likely to screw it up. So we really wanted to have science missions, but if you make a completely manual spacecraft, you have no scientists. You also have the potential for catastrophic accident. So the standard engineering philosophy of the United States at the time of building the Apollo spacecraft was, if a human could do it, the machine should not do it, but the machine should relieve tedium. So the machine should do things that a human could not do. The machine could determine that an RCS jet, which changes attitude and whatnot, was not firing and could then adjust. Now, a human can technically do that, but it takes about 30 minutes and a guy staring out of the window going, hey, boss, that jet isn't firing. But the computer can tell that immediately. However, landing on the moon is a job for a human, because even though a computer can do it, it is something that a human can do and should do. So that's kind of the standard philosophy. The machine should not take over from the human. The human is supreme. But the Apollo guidance computer is tasked with integrating all of these extremely complex systems. And you can see sort of a diagram, and this is a simplified diagram of what the Apollo guidance computer does. In the middle, you have the guidance computer, reaction control jets, all of that stuff. The very interesting thing is the Apollo guidance computer is not just an integrator. It's also a fly-by-wire control system. So fly-by-wire just means that you don't actually fly the spacecraft manually. What you're doing is you're flying an idealized model inside of the computer, and then the computer makes up the difference for you. So every time the pilot puts his hand on the stick, he's not flying the spacecraft directly. He is having his commands moderated by the machine. It also manages all the analog and digital displays. So these are the displays that the astronauts see, and it's a hugely complicated thing. These are all switches, toggles. Even though the entire spacecraft is digital, there are analog displays because of human limitations. We actually do very well if we see some things as changing dials versus just seeing them as numbers that get spread across. So the Apollo guidance computer was originally designed in 1961, and it does all of these very complicated things with just 5 interrupts. It has a 1 megahertz clock. It has 16-bit words, one parity bit, and 15 data bits. It has 248 words. I didn't drop a K. 248 words of RAM. It has 36K words of ROM and 17 registers. It weighs 70 pounds. It's 1 meter cubed, and it draws 55 watts, which is basically what a modern laptop draws. Now, when I said it was 70 pounds, there was a little bit of laughter, and that sounds like a really heavy computer, but this was the state of the art at the time. This is the real-time computing complex which sat in the basement of Houston. This is what the Deep Space Network used to do all of its computation. This computer takes up 2 floors. It draws half a gigawatt of electricity. Its waste heat requires a refrigeration system, and it's easily several thousand tons worth of computing equipment, equivalent machines. Questions after? So the AGC is a digital computer, and there have been other computers. This is ENIAC. This is not the first digital computer. The main advance that you see in the Apollo guidance computer is that it's made out of integrated circuits. So this is a flat pack circuit. It doesn't look like an integrated circuit that we would see now because we use a slightly different technology. But integrated circuits were brand spanking new. They were so new, in fact, that NASA had to figure out how to do quality control on integrated circuits. My favorite test that they did was they would take the batches of integrated circuits, they would weigh them very precisely before, and they would dunk them into liquid Xeon. And they would leave them there overnight, and they would pull the chips out, and if the chips were slightly heavier, they would reject the entire batch because Xeon had leaked into the chips. The Apollo guidance computer uses core rope memory. So core rope memory is, you have a magnetic donut, and then you have a piece of wire that either goes inside of it or outside of it. If it's outside, it's a 0. If it's inside, it's a 1. So that's where the ROM is. And it's ROM because somebody has to sew this. Somebody has to sit down at a loom and sew this. So these are the star charts, these are the programs, these are the other bits of data that can't be overwritten. So the interesting thing, when the programmers would program, they would take their AGC assembly language and they would hand compile it into zeros and ones, and then they would take a stack of zeros and ones to a loom operator who would then weave this into the computer. So this is the Apollo guidance computer. This is the Apollo guidance computer on the far right-hand side. It's a shoebox, basically. And then what you see next to it is called the diski. And the Apollo guidance computer is also interesting because it's one of the first interactive computers. So before this, you would take a shoebox full of paper tape, and you would sort of feed it into the machine, and then you would come back. There was no sense that you could have this interaction, that a human could have an interaction with a machine. It was just sort of unheard of. People have been sort of playing around with that idea, but only in their minds. And the Apollo guidance computer was one of the first one designed to be interactive. And you did this through the display keyboard, or they shortened it to diski. So the diski is quite interesting because it is the first example of a user interface for a human for a computer. It's also the first example of a human interface for a human in a spacesuit. So it's hard to show you the scale here, but each one of these buttons are about this big because you have a big sausage finger that you gotta push. So the diski allows the AGC to give fast updates to the astronauts. So you can kind of see, and I'll zoom in a little bit, but you can kind of see there's a whole block of numbers here that don't make any sense because we're not trained to use the diski. This updates, and the diski makes a really wonderful sound. It's built out of micro relays, so whenever it changes the numbers, it makes one of those wonderful old tick-tick-tick-tick sounds that you see in ferry buildings and train stations. But it's able to change relatively rapidly. So if an astronaut calls up a program that says, what's our attitude change based on this firing, the computer is able to say what the drift of the attitude change is. It also allows the astronaut to run select programs. So to zoom in a little bit, you can see on the top right-hand side, prog stands for program, or master program. And then you see verb and noun. So verb is the command that you are giving to the machine, and the noun is the information that you are giving to it, or the prompt to ask you for more information. And then up at the top is the active program. So this is a diski that is waiting to take off. It is sitting on the pad. Program 00 is I'm waiting for the Saturn V to give me control. You can see also on the far right-hand side that there are some more indicator lights. And the one that I want to call attention to right now is gimbal lock. So the computer, before you would get into gimbal lock, would start furiously beeping this thing at you. Like, watch out, you're going to hit gimbal lock. And the other one is uplink activity. So that's right there. Uplink means that NASA, that ground control, is sending you information through the deep space network. And you would see this blip every so often. It's just so the astronauts know what's going on. And the question is, what is the computer actually doing back there? So the astronauts are trained not in computing. Gus Grissom, who sadly died in Apollo 1, was one of the first astronauts to be trained in the computer, and the poor schlub from the MIT instrumentation laboratory came to explain it, and he started giving a breakdown of hardware, and he started explaining how the hardware worked, and then Gus Grissom stood up and he said, God damn it, I don't need to know how to run a computer, I just need to know how to operate it. So the AGC is primarily predicated on interrupts, and it's predicated on 6 interrupts. So this is the view of what the AGC is doing within 1 second. So the AGC is a relatively slow computer, so we can actually visualize it on second intervals instead of 1/1000th of a second. So the first 2 interrupts are mission time. So they're flipped, the words are flipped. Time 1 has a period of 10 milliseconds. So every 10 milliseconds you have a clock tick. And that clock tick overflows, it's 15 bits, every 164 seconds. And that flips over into the high word. So this runs out after 3 months, but it doesn't matter because you're not going to be in space for 3 months. But this is how, when the clock starts running, this is how you keep track of time. So there is only 1 clock, and it is kept by the AGC. So time 3 is the wait list. So the wait list we'll get into a little bit more, but it is the fundamental lowest level for the tasks that need to be run by the system. The wait list is also on a 10 millisecond interval. T4rupt is it's interrupting every 20 milliseconds, and it runs for a little while. T4rupt is interesting because it is the thing that is waiting for astronaut input. So it's basically what runs the diski. So they had to give it its own specific interrupt, and they didn't want to originally, but they had to give it its own specific interrupt because they found that astronauts were getting impatient because the computer was doing other things, and they're very slow. Humans are very slow, but the astronauts wanted immediate response, so the human gets their own interrupt. The digital autopilot also kicks on very quickly, every 20 milliseconds, and the digital autopilot is the thing that keeps the attitude of the ship while you're traveling. And it kicks on, and it is the highest priority task in the system, and it runs anywhere from between 10 milliseconds to 120 milliseconds, which is an outrageous amount of time. And then the fine scale clock. And this is actually a sub-millisecond clock in the machine, and it's programmable by the digital autopilot. So the digital autopilot kicks on every 20 milliseconds, which is an eternity if you are firing a rocket engine. So what they do is they have something that is sub-millisecond so that the digital autopilot can say, I have a job, and it needs to update every millisecond. And that's how they do rocket fires. So time 3, time 4, and time 6 are programmable. So jobs that are running in this computer can take these interrupts and say, I need them to fire at a certain rate, or I need them to fire now, or schedule in a general manner. So nowadays, we would call the AGC a priority scheduled real-time embedded computer, which is a bit of a jargony thing to get your word around, but we actually have words for these things now. At the time, they had none of these words. And we'll sort of see that priority scheduling was actually invented for the AGC. Before this, all you had was round-robin time batching. So you would say, each job has 10 milliseconds, God bless you, and then go round and round and round. So it was controversial to actually have the AGC do priority scheduling because it had never been done. And Hal Lanning is the MIT Instrumentation Laboratory employee that suggested it. At the time, I believe he was a graduate student. So people really weren't having that, but the Charles Draper just said, well, he's very smart, and he says it, so it goes. Now we don't think anything of priority scheduling, but this was outrageous. So there are two tables that exist for jobs in the Apollo guidance computer. And the lowest level one is the wait list, which we sort of talked about. And by convention, and there's nothing to enforce this, but it is mandatory, each of these jobs has less than 4 milliseconds of execution. So because the clock is so slow in the AGC, this is actually about 120 instructions that each one of these jobs are allowed to run before they must stop. It has a 9-task limit. So in the wait list, the computer can only do 9 things. If you try to get it to do more than those 9 things, it will fail. The wait list is nice because it's not programmable. It's baked into the core rope memory. So you can verify before you fly the thing that it'll only try to do 9 things. It has very basic instructions. So the AGC is a very primitive computer. It had a primitive instruction set even for the time. And there's no rescheduling. So if a job needs to, if a job on the wait list decides that it needs to be rescheduled at a slightly later date, it can't do that. So each one of these things have to run on a fixed interval. And it has no executive. We haven't talked about the executive. So what is the executive? The AGC software provides 2 operating abstractions. So the wait list is the lowest level, it's terrible, it's tedious, and you can't work that way. So in software, they built things to make their job easier. They didn't call it an operating system because operating systems hadn't gotten to the MIT Instrumentation Laboratory yet. They didn't know they existed. So the executive has low-level routines. We would now call them functions, but they called them routines at the time. They're very low level. They're take a bit of memory, fiddle with it a little bit, and then store it in another bit of memory. But it saves time because you can repeat these things. It does system restarts. So the executive is responsible for running jobs, and if it notices that the job is taking too much time, or if it notices that the job has failed, it will reboot the computer, or it will reboot the job, depending. It has supervision, so it's capable of telling that a job has failed in a bad state, and then restart it later. So if a job has failed in a bad state but scheduled itself to run in another 120 milliseconds, that can't be allowed because it probably didn't do the right thing, and it keeps the core set. So the core set is another one of the priority scheduling task queues, and it's limited to 12. And the interesting thing about the core set versus the wait list is that the core set is programmable. So at runtime, the software that's inside of the AGC can add more and more things to this core set. Now, there's nothing to stop the core set from filling up. You've only got 12, and by convention, you should never go past 11. But there's no invariant in the system to mandate this because the system does not have spare resources to do this sort of thing. And you see that all throughout the Apollo guidance computer. Most invariant guarantees are left to analysis and testing. So the way they would test is they would simulate this on a Honeywell mainframe, and they would have an astronaut sit in a mock-up of the Apollo spacecraft and then fly the thing. And if it killed them in simulation, they went back to the drawing board. So the core set is priority ordered. This is where priority scheduling comes in. So each one of these jobs has a metadata tag of 7 bits, and it tells you the priority, the relative priority of these things. So the AGC, when it gets interrupted periodically by T4rupt, will go through and it will pick the job with the highest priority and it will run it for 20 milliseconds. And if this is not enough time, too bad. So the 20 milliseconds interrupt happens, and then you have the option to use the interpreter. So the executive is very low level. You have very basic instructions. So what is the interpreter? So the native instructions from the AGC, they don't give you that much. You can add, you can subtract, you can divide, and you can fiddle with memory, which is great if you're doing accounting, but it's terrible if you're trying to figure out rendezvous accelerations. So also, the AGC word size for data is 15 bits, and that's insufficient accuracy for space flight. So when they designed this thing, they thought, it's approximate, it'll be enough, and they realized after the fact that it wasn't enough. So they built the interpreter, and the interpreter gives you high-level routines. So you have, instead of having to manually do cross products, there is a function to do cross products for you, which at the time was revolutionary, especially on such a very tiny computer. It has a rich instruction set. So not only do you call out to a function to do a cross product, you can have a pseudo instruction that does that for you. The interpreter itself is a routine in the executive that takes what we would now call a string. And that string is just a list of interpreter instructions because we're just working with assembler here. That was also new in the Apollo guidance computer. It has extra wide words. So it has 32 data bits to represent, which is insufficient accuracy to get anywhere past the moon, but you only need to get to the moon. And it's radically simpler programming. So you have higher level, which we would still consider to be very low level, but you have higher level constructions now. So you have an Apollo spacecraft, and it's in a free return orbit. It's going to whip around the moon. So you have to do what's called capture braking. So you flip yourself around and you fire opposite to your acceleration to slow yourself. And this has to be done by the computer. And it has to be done by the computer because the computer has to calculate what's happening to the orbit of the spacecraft while this is happening. So capture braking, you fire opposite to your acceleration, and then eventually you achieve lunar orbit. So up to this point, loss of the command module computer hasn't been abort worthy. So the lunar module separates, right? So there have to be 2 computers because there is no such thing as a remote network at this point. You have radar that can sort of beam you 5 bits, but not a remote network. So there are 2 computers. One is in the lunar module, one is in the command module. And you can technically lose the command module computer, and they will attempt the mission. It's a different matter for the lunar module. So in lunar orbit, the lunar module separates from the command module, and the command module pushes itself into a slightly higher orbit because the command module has a lot of fuel. The lunar module is an aluminum balloon with just enough fuel to not kill you. So the lunar module computer is absolutely essential to the controlled landing on the moon. At no point does the astronaut manually fly the lunar module. It's all fly-by-wire. So at the top of the orbit, once they've separated from the service module, program 63 fires the LM engines. So again, they're braking by firing an engine against their acceleration, and program 63, an astronaut punches that in, hits prog for progress, and then that fires, and then they start to descend. So this is what's called the high gate, if you ever read any more about the Apollo project. Of interest, the routines in the Apollo guidance computer had names. The name for this routine was Burn Baby. Apollo 11's core set overflowed here. So as soon as they did this, the Apollo 11 computer tried to schedule more tasks than 12. This caused computer restarts. So it caused the computer to crash and then bring itself back up. It turns out, so we've sort of blamed Buzz Aldrin for a long time that it was his fault for leaving a radar on. But it turns out we can now actually accurately simulate the Apollo craft in a computer and then make it run run the AGC, it turns out that no matter what Buzz Aldrin did, that still would have happened. There were two cables that ran side by side, and they happened to be phased slightly wrong, so that when a signal went through one cable, it caused an alternate signal in the other. And one of those cables happened to be the radar rendezvous cable. So the computer continually saw updates from the radar that the radar wasn't actually sending because the radar wasn't close enough to the moon, and it ate up 80% of the computer's processing time, just dealing with those errant signals. Now, if the Apollo guidance computer had been round robin, the Apollo 11 lunar module would have crashed into the moon. But as it happened, because it was all priority scheduled, the computer was able to take all of those interrupts and schedule the most important tasks, which at this point were program 63, because you needed to have controlled descent. So priority scheduling, if it had not been invented for the AGC, we would have lost the astronauts. So eventually they leave the high gate and they enter what's called the low gate. They're within 5,000 meters of the lunar surface, and they run program 64. And I say they because the astronauts call this up. The astronauts are in control. And the program 64 pitches the spacecraft so that now the astronaut, the pilot, can see out of the window. Before, they were pitched on their back and looking up into space. So this is a waste of fuel. If you were going to automatically land, you would never do this. But because we want the astronauts to be able to be in control of the spacecraft, we give them the ability to look out of the window. All the lunar modules that ever flew had a potentially fatal bug, and this is my favorite bug in the Apollo guidance computer spacecraft. It turns out the radar is designed so that it detects that it's landed from a certain signal. If you happen to fly over a crater that is shaped in a certain way, it will cause the radar to erroneously detect that it has landed, and the Apollo guidance computer has no way to check that the radar is correct. It just assumes that it's correct. When the radar sends the signal that says that we've landed, it shuts the engines off. So had they flown over 3 craters that exist on the moon that would cause this bug, there are only 3 of them. Had they flown over one of these, they would have shut off the radar, and then they would have died. Actually, they would have aborted because they were high enough, but they might have tried to recover, and then they would have died. So the last program is program 66, and it steadies the thrust vector. So steadying the thrust vector is kind of a jargony way of saying it allows the astronaut to control the rate of descent. So in Apollo 11, Neil Armstrong has to change where they're going to land, and he does this while they're doing program 66. So they are still descending at a rate that the astronaut is controlling. So they're descending at, say, 10 meters a second, and then you want to descend slower and slower and slower, so you eventually touch the lunar surface. So if any of you played with industrial control, this is a PID controller. My second favorite bug in the Apollo guidance computer has to do with this PID controller. So if you've ever worked with PID controllers, you know they can be erratic if you feed the wrong signals in. So the stabilization of the engine is done by a PID, but it's erratic. So it's just barely stable. So Apollo 11, 12, 13, and 14 had an engine thrust that was almost not quite stable. So they almost flipped over on their side and crashed. But they didn't. We landed on the moon. The only one that we missed out on was Apollo 13, and that was the fault of the service module because an oxygen tank burst. So the AGC is interesting, but why study it? The sort of question comes up, who cares? I mean, it's interesting, but why study it? And sort of the easiest answer is it's because the AGC was barely possible. So that device you see behind there is 5 tons. It is the instrumentation unit for the Saturn V. It's what controls the Saturn V flight. It's tall enough that I can stand inside of it and reach up and still not quite hit the top. It was so heavy that they turned the computer for the Saturn V into a structural element. That computer has basically the same capability as the Apollo guidance computer. So if you compare something that's 5 tons versus something that is 70 pounds, few believed that the Apollo guidance computer could ever be dependable. We had very little experience with fly-by-wire systems. So this is the X-15. It is a rocket plane. It goes to space. On the ass end of it is a rocket engine. It is the first craft to ever be flown fly-by-wire. So it is the first spacecraft, and Neil Armstrong actually did the first flight doing this, where you flew an idealized spacecraft. Because it turns out when you're re-entering the atmosphere in a craft like this, it's very easy to skip off the atmosphere. The X-15, when flown under totally manual control, would bounce off the atmosphere several times and then descend back down because it didn't have escape velocity. Few believed it could ever be dependable. Some of the research experience in the X-15 suggested that it could be, and it was. The Apollo guidance computer never caused a craft loss. It never caused an abort. So how did they actually do this? And this to me is the very interesting question. How do you take something that's so primitive under such constrained circumstances, and how do you make it not kill people? And the way that they actually did that was they had careful, pragmatic, and empirical engineering. So every change they would make, they would stick an astronaut in a mock-up, a complete mock-up, and they would have them run through it, the entire flight checklist, because nothing was unscripted. Everything had a checklist. So every bug that we've since discovered had to be discovered by flying millions of missions against the moon, because we can simulate, physically we can simulate the Apollo craft, have this computer run inside of it, and land arbitrarily on the moon. This sort of engineering is very common in aeronautics, and many of these people were aeronautics engineers. You see it less in software, and it's sort of interesting that, at least in the Apollo guidance computer, aeronautics engineering, their methodology fed into what the instrumentation laboratory employees did. So they started out with 3, and they eventually turned into 400, but they kept that same very rigorous proof by exhaustive testing. And the techniques that were developed for the AGC are still in use today. We call them different things, and they're so fundamental we don't really notice them. So this book, Real-Time C++, Efficient Object-Oriented, so on and so forth, it discusses priority scheduling, and it never mentions the AGC. It discusses dealing with machines that have odd bit size, and it never discusses the AGC. Because it doesn't need to, because they've become such foundational principles to software engineering, to embedded systems engineering, to software engineering in general. And the interesting thing to me, the last interesting thing is that, the past informs our present. Whatever we do in the past sort of sets what we can do right now. So because James Watt figured it would be real great to build a thing that could pump water out of a coal mine, we had the Industrial Revolution. And because we had the Industrial Revolution, we had the Information Revolution, and so on and so on. Wherever we sit beholden to the past, to the work, the innovations that the past has made, and we sit inside of this great project. And in the Victorian period, they would capitalize great project because they meant civilization. And I don't necessarily mean civilization. I mean, the techniques that we develop today to, say, get to Pluto are the foundations of the future. Whatever we invent today, whatever we take from the past and use in the present informs what people that come after us can do. So human civilization, all the way from the Cro-Magnons on, from the first Cro-Magnon to look at a hand axe and go, man, I wish this thing didn't cut my hand so much, all the way to the people working in the AGC, they're all looking at the past, taking the technology and doing something new. And the thing that we have for us is that whatever techniques that we develop today, dependent typing, however it is that we can influence the future by building new things, we are able to give the future more tools to do interesting stuff, to get outside of the planet, to end poverty. And that, to me, is fascinating. That's primarily why I'm interested in studying the Apollo guidance computer, because it's an example of people who are trying to do a very specific thing. And they think it's pedestrian. They don't think it's that special. They don't think it's outrageous. They think they're just very busy and very hurried. And a lot of us, I'm sure, feel very busy and very hurried, but what we're doing is actually very interesting. We're living in a very unique time. So I would encourage everybody to go out and build something fucking amazing. Thank you. Incidentally, this is Margaret Hamilton. She is standing with a printout of the Apollo guidance computer, program Colossus, which ran inside of the command module. She was the lead software engineer for the Apollo guidance computer software effort. She is pretty tall, so that's a lot of source code.
Yeah. You said the AGC was £70. I believe that includes the very heavy case.
Yeah. So the case was hermetically sealed. So the Apollo guidance computer comes in 2 variants. One is the Block 1, one is the Block 2, or the other is the Block 2. So version 1, version 2. Block 1 is completely open, meaning that every human that breathes around it can get moisture into it. So originally they thought that they would ship up 3 computers. And if the computer failed because they had no faith that a digital computer built on integrated circuits could run for more than 2 hours without burning up, what they would do is they would have the astronauts service the machine, pull bits and pieces out and solder and so on. Eventually, NASA got comfortable with the idea that this thing could run for at least 3 weeks, and so they ripped that out. And so Block 2 was hermetically sealed. The reason that they went to a hermetic seal, which drastically increased the weight, was because in Gemini, the computer was not sealed, and they had a computer failure because someone urinated on the computer. Microgravity is very hard to deal with waste, and some of it escapes. So the computer shorted out. So NASA now hermetically seals all of the electrical systems inside of spacecraft. And the metal that they had available to ground the computer was aluminum, and aluminum is relatively light, but it was 30 pounds worth of aluminum to seal the thing.
Questions?
How much thought and sort of experience, trial and error, went into engineering the sort of user interface from the initial version to the one that they actually used on the mission?
Yeah. So the first contract that was ever awarded for the Apollo craft was for the Apollo guidance computer. So you have Kennedy, who gives this famous speech in '61, and NASA signs up or is obligated to go to the moon in late '61. And by December of 1961, there is a contract for the AGC, because they recognize very, very quickly that they need to have an integrated control system. At this time, they're thinking that they're going to do direct descent. But even still, they recognize that they need to be able to land on the moon, and that's a very difficult thing to do. So they need a computer. Eventually, originally, the Apollo guidance computer was meant to just be in the lunar module, but eventually it moves also to the command module to save time, basically, in terms of engineering. So from 1961 all the way to 1969, you have 8 years. But really, the control system had been developed for the Polaris in '54, something like that. So round up, say, 20 years.
Was the computer built by NASA, or was it built by a contractor, and if so, who?
Yeah, so I believe it was Raytheon that fabricated. So NASA was a systems integrator. NASA's main deal is that it is an integrator of systems. Marshall Space Flight Center has in-house experts. They're the people that build the rockets. But even they don't actually build the rockets, they build the prototypes. For the computer, NASA contracted out to, they're now called Draper Laboratories. They contracted out to Draper Laboratories. Draper Laboratories designed the computer, but then they contracted out to Raytheon to build the thing.
So it was built in the Boston area, basically.
Yeah.
So we're out of time. Lunch is now. I'd like to just invite people to stay and talk to Brian about this if they're interested, but I also want to let you go if you want to get some lunch. So thank you, Brian, for that amazing time.
Thank you.
Great stuff.